Hello everyone. This video is about the modeling of dual Agno bridge converter. We have already seen in another video that MATLAB simulation of dual Agno bridge converter in closed loop mode. This video is about modeling of dual Agno bridge converter. The circuit of the dual Agno bridge converter is shown here, which has an input bridge and an output bridge. These two bridges are connected through a linear transformer whose transformation ratio is taken as 1:1. We have two energy storage elements L and C. One is in the input side, another one C is in the output side. So there will be two state variables, and we can have two state equations. And to write the state equation for the L, we need to have a KVL equation. And to have the state equation for C, we need to have a KCL equation. And we are going to write the KVL equation by using the voltage across the inductance. We have switching modes S and Q. S is the switching mode of the bridge 1, which can take its value as +1 when S1 and S2 are in the on condition, and the S value will be equal to -1 when S3 and S4 are in the on condition. Similarly, Q can take +1 when Q1 and Q2 are in the on condition, and it can take -1 when Q3 and Q4 are in the on condition. Now we can write the KVL equation in the input side. So KVL equation, the voltage across the inductance L, it can be written as L into dIL by dt. That is equal to S times the input voltage Vi minus Q times the voltage across the capacitance, that is the voltage across the second bridge. So we can write the first state equation, which is dIL by dt equal to SVI minus QVC divided by L. Similarly, we can write the state equation for capacitance by taking the KCL, that is Kirchhoff's current, by applying Kirchhoff's current law at this node. So at this point, we can write the current IQ, the current which is flowing, which is coming out of the second bridge will be Q times the current which is flowing through the primary side of the linear transformer. So we can write QIL equal to the capacitor current plus the output current I naught, so we can write the current through the capacitor as QIL minus VC by R. The current through the capacitor can be written as C into dVC by dt. The VC is the voltage across the capacitor. So we can write the second state equation as dVC by dt equal to QIL by C minus VC by CR, as I naught is equal to VC by R, or it is V naught by R. VC and V naught are same. Now we can write these two state equations, that is dIL by dt equal to SVI minus QVC by L, and dVC by dt equal to QIL by C minus VC by CR in terms of matrix, in the matrix form. So this is the state equation in the matrix form. We all know that state space model of any system can be written as X dot equal to AX plus B, U, where U is the input matrix, X is the state variable matrix, state matrix, and A dot, the state equation, which can be written as X dot matrix is this one. So X dot matrix consists of dIL by dt and dVC by dt. There are two state variables, and this is the state matrix A, which is that into the state variable vector, which is IL and VC, and this is the B matrix, which is the vector here, and the input variable is VI. We have only one input variable. So the state space model, which is written in the matrix form as dIL by dt, dVC by dt equal to A matrix consists of 0 minus Q by L, Q by C minus 1 by CR into the state matrix, which is IL and VC, plus the B vector is nothing but S by L 0 into VI. Since V naught is equal to VC, we can write the state space model in terms of V naught as dIL by dt, dVC by dt equal to 0 minus Q by L, Q by C minus 1 by CR into IL V0 plus S by L 0 VI. So this is the state space model of the dual active bridge converter, which consists of two energy storage elements, L and C. So we have two state equations. One state equation is in terms of the first equation is obtained by applying KVL equation for in the inductance side, and the second state equation is obtained by applying KCL equation in the capacitor side. So this is the state space model of the dual active bridge converter. Thank you.